Hi. So today we will be learning the relationship between electric potential and electric field. As we know that the two physical quantities, electric potential and electric field, both are defining the same physical entity, the space all around a charge. So let us today see what is relationship between electric field and electric potential. So let me start. Suppose you have a charge, and due to this charge along its radial line you have some potential at one point V plus dV, okay, and at a further distance, if you go further dl distance, a little bit distance, small distance, then obviously the potential will be reducing, and then the potential becomes V. So we know that potential with distance reduces as potential is equal to 1 upon 4 pi epsilon naught Q, this is capital Q, upon R. When this R increases, potential reduces. So let the potential at point A and B, okay. Potentials at now we assume distance between A and B is very small, equal to dl, so that electric field remains same almost. Now let us find work done in moving a charge from B to A. Okay, test charge Q naught from B to A by external force the dW, okay, for a small distance. Okay. A small distance dl is, if this is equal to dw, then it is equal to, now see here, the two charges are, one is Q and other is small q naught, both are of same sign. So if some external body is bringing it near to capital Q, then it will have to do some positive work. This will be positive. So F external dot dl. Now we do not know what is force external. We do not know, but we know that force external is equal and is opposite to force electric. So we can replace this. Therefore dW is equal to minus force electric dot dl, and this is equal to minus force is equal to QE. So this becomes equal to dl, Q not E dl. Now it is not potential, because we know that change in potential, which is equal to final potential minus initial potential, and finally it is reaching to A. Final potential, okay, let me write final first of all. Final minus V initial, and this is equal to VA minus VB is equal to minus Q naught. Okay, let me include one more thing. Let us include one more thing, and this change in potential is equal to change in potential energy per unit test charge, and this is equal to work done per unit charge. Therefore VA minus VB, it comes equal to, okay, minus Q naught E dot dl upon Q naught. So therefore change in potential del V is equal to, we obtain E dot dl. This is your change in potential. Now if you have to take the charge for larger distance, therefore for larger displacement of test charge, movement of test charge, we will integrate the equation. Therefore del V is equal to VA minus VB is equal to, and we are taking charge from B to A. From B to A. So here you are writing VA minus VB, but here you will be writing from B, integrating from B to A. So it is minus E dot dl. Okay. So this is relationship between change of potential and electric field. Now one more thing, that E from the equation, E is equal to dV upon dl. dV upon dl. Okay. So if E is equal to 0, then it is differentiation. Then V is equal to a constant. Inside an electrical cell, inside a charge cell, for example, we had obtained that E inside is equal to 0, and there is electric field on the surface, and outside the surface. So electric field exists on the surface and outside at any point the surface. So here when electric field is 0, so potential is a constant. So let me find electric potential due to a cell. Due to charge Q on a shell. So as we know that V is equal to, suppose it is having radius R, and here you have a point A, and outside the spherical shell you have point B, and inside at any place you have point C. Okay, so we will be writing potential at all the 3 points. So VA is equal to, from definition, from formula, it is equal to 1 upon 4 pi epsilon naught charge, and charge we can suppose that it is centralized at the center. So the charge will be Q upon the distance is R only. Now at a point B outside the sphere, which is at a distance x, okay, it is at a distance x. So VB will be equal to 1 upon 4 pi epsilon naught Q upon x. Now VC. So we were finding for VC, we'll find potential difference. So del V is equal to final potential at final point minus potential at initial point. And we know that this is equal to EdL. Now this electric field inside the cell is equal to 0, this 0 into dl. So you will find that okay, VC minus VA is equal to 0. It implies that VC is equal to VA. So potential inside any surface is same as potential on the surface. Therefore, potential at any point inside the spherical shell is equal to potential at the surface. Okay, this is another thing. Equipotential surfaces. So next topic is this. So let me first of all write the formula of electric potential. V is equal to 1 upon 4 pi epsilon naught Q upon R. So for a point charge, you can see in formula everything is constant except R. So For a point charge, if you make R also constant, it means if you take a sphere which has same radius all along, so you find that potential on the surface is same. So in this way you can obtain the equipotential surfaces for a point charge. Are concentric spheres. Okay. Concentric means it has all along same potential. If potential is V1, at every point you have potential V1 only. Let us take another concentric sphere. If it has potential at one point V2, then at all the points as R is same, so whole potential on this sphere you can find is same. So at every point you have same potential, that is V0. So for a point charge, equipotential surfaces are concentric spheres. Now second one, for uniform electric field which is along positive x direction, here electric field is in positive x direction. And one thing more I would like to explain here, one thing more, let me do it with the help of a sphere, concentric sphere. So electric field is in radial direction and uniform potential is there on a sphere. So equipotential surface for this point charge Q will be the sphere itself. Now go a distance r along radially outward direction. Go a distance r, this distance, and go along another direction the same distance r. Both are same. Now at which point you will find the potential lowest? At this point P or at this point S. Look here, S is closer to pure charge Q. It is closer. So here denominator is less. Okay, let me write formula. V is equal to KQ upon this R1, and here you have R2 if. So in first case, for potential at S, it will be R1 only, and for potential at P, it will be KQ upon R2. KQ upon R2. So small denominator, you can find that denominator in case of V potential at point P is small. Okay, it is large, so potential will be small. So change in potential is steepest in a direction, and the same is the direction of electric field at that point, because at this point you can find that direction of electric field is along this one, and potential also changes to its steepest. So from here we can note that electric field is in direction in which the change in potential is steepest. Okay, so So this is not, let me write here. Okay, so now we will be finding equipotential surfaces for uniform electric field. Here you could see that electric field is in radial direction and equipotential surfaces are on the surface of spheres. So we see that the tangent direction, this is your tangent direction in this very figure, and radial direction are perpendicular to each other. Radial direction and tangent direction are perpendicular. So we can assume that if field is in x direction, electric field is along, okay, and this is your I cap along x direction. So equipotential surfaces should be in yz plane. So let me draw equipotential surfaces. All the equipotential surfaces would be in yz plane. Along x-axis is in yz plane. Okay. Now suppose you have a dipole and you have to find electric potential surfaces due to this dipole. So you could see that V is equal to kq upon L. If this length is 2L, so at the center it will be due to positive charge, and due to negative charge you will find that it becomes minus kq upon L. Minus kq upon L. So V at center, V at O, on adding, when you add, V at center becomes equal to 0. So you find that there is no potential at origin, so you cannot draw any equipotential surface at the origin. So let me draw here equipotential surface. Here you have negative charge, here you have positive charge. So the surfaces will be, little bit contracted near to the charges along this center, and here it will be expanding. Here contraction, here expansion, and you will find that at the center there is no potential, so there is no any equipotential surface. So along center these equipotential surfaces will be contracting, and away from these dipole moments they will be expanding. So this is the nature of equipotential surfaces. Due to a dipole. Now if here you have potential V1, at every point you have potential V1. On this surface if you have potential V2, at every point you will have the same potential V2 only. And if you have at one point potential V3, so all along on this surface you will be having same potential V3, and same will be case here. So now equipotential surface for two like charges. This is your fourth case. Plus Q and plus Q. Now look, let us use the formula. V is equal to KQ upon R for both the charges. So V at center, at this point, at center. Let me take one central point at O, plus KQ upon R. So it is increasing, you can see. So when it is increasing, so you will see that equipotential surfaces will pass through center and it will be touching from each other. So here it will be displaced because potential is large along this line. So let me draw a line closer to this charge as potential has increased. And so let me draw, and here it will be going away from it. It will be going. Let me draw again. You have two charges, plus charge, plus charge. So you have let me omit once again. This will be the nature of, means they are expanding from each other, and here they are expanding, and this way they are coming close to each other. The same will be here. So this side they will be expanding. This means that very close to this very charge along this side, you will have same potential as what the potential is at a far distance here. This is all about equipotential surfaces, and this is a very useful concept I am going to use in doing numericals. So let us do one numerical on all these concepts. A uniform electric field E of 300 Newton per Coulomb. You have electric field of magnitude 300 Newton per Coulomb is there along negative x-axis. A, B, C are 3 points and coordinates are given in meter. Here you have coordinate given in meter. Find potential differences VBA. So you have to find 3 things. First one, VBA. Second one, VCB, del VCB, and finally you have to obtain del VCA. Del VCA. So first one, del VBA is equal to minus E dot dr. E dot dr. So let me do. So you have electric field in negative x-axis and this is of magnitude 300. Okay, this is in Newton per coulomb SI unit, and dr is from, you have to go from B to A. Okay, from B to A, and this is, you can see, equipotential surface, and displacement between, from going from B to A, and this direction, negative x-axis direction, there is 90 degree. So from going B to A, and it is going 4 minus 1. Okay, so 4 minus 1, and this is in SI unit, in meter, and E dot dr, so it will be cos theta, and cos, this is 90 degree, and cos 90 is equal to 0. So you can see that change of potential from B to A is 0. So when you are proceeding along the equipotential surface, why equipotential surface? As it is perpendicular to electric field. The surface take note of this, the surface is perpendicular to electric field, so this surface is equipotential surface. Therefore, work done in bringing any charge on equipotential surfaces is 0. Work done in bringing, work done is equal to, okay, work done is equal to, let me minimize it, V initial, V final minus V initial, work done per unit charge. And this is same, V minus V is equal to 0. So no work done, therefore change in potential energy will also be 0, and change in potential will also be 0. So sometimes you will be doing only by statements. You need not to solve this question. So when you see that the surfaces are equipotential surfaces, so you can immediately write that, okay, there is no potential difference between the 2 points. Now next question, from del VCB. Del VCB, okay, and this will be equal to minus electric field dot dr. Now electric field is 300 in SI system, 300 dot, and dr is from C to B, from C to B. We are going from C to B, and this distance is on x-axis 4 minus 3. This distance is dr is here. On x-axis here, let me write down, dr is equal to x final minus x initial, x-axis, and this is your 4 minus 3, and this is equal to 7. Okay, so you will be using this into 7, and it is going from C to B. Okay, from C to B, this is in outward direction, from C to B is in this direction, and electric field is just in opposite direction. So here you will have cos 180 degree, and this is equal to minus 1. So minus into minus plus 2100 volt. And now question number 3, you will find potential difference from C to A, del V CA, okay, is equal to, now look on diagram, CA. You will not find displacement dr along this direction. You will not be finding dr. So in such cases, you will see that the point A is on same equipotential surface as B is there. So work done will be same. Therefore, no work done in bringing from point B to point A. Okay. Therefore, as potential, they are all same potential. So you can write that since VB is equal to VA, equipotential surface, so you can write from this second question that del V CB is equal to del V CA, and this is equal to your 2100 volt only answer. Next question. Is the potential in the region of space around the point given -1 meter, 2 meter, 3 meter is given by this much. Calculate the 3 components of electric field at this point. So first of all, we will be writing formula. Electric field is equal to minus dV upon dx, or whatever, dV upon dr, let me write. Now electric field along x-axis will be equal to minus dV upon dx only, and this is equal to minus d, and V is given here. V is given 10x square plus 5y square minus 3z square. Okay, let me tell you one more thing. Let me write here del. And the meaning of del over here. Here, del means that it is differentiated with respect to x only, and rest things are like y value, z value are taken as constant. So whenever you will have del in place of d only, this also means differentiation only. But this is differentiation only with respect to x, taking y thing, z thing constant. So let me differentiate. This is equal to minus and 20x. And if you differentiate any constant thing, you get 0. Therefore, Ex at, you have given point -1 meter, -1, okay, at -1 meter is equal to minus 20 into -1 is equal to 20, and this is your volt per meter. First answer. Now second question. E dy is equal del, okay, let me write the value of electric field 10x squared plus 5y squared minus 3z squared upon del y. Now this del y means take other things constant, x things, z things take constant, and you will be differentiating only with respect to y, the y term. So this becomes equal to, okay, here is a minus sign also, minus 10y. Okay, let me write one more thing, 0. This is constant, we are taking it constant, so 0 plus 10y plus 0, and this is equal to minus 10 into, and y value is given, this is 2 meter, y value is given, therefore electric field along y is equal to minus 10 into 2, and this is your volt per meter, so this is your minus 20 volt per meter, answer. And third one now, third one, you have to find electric field along z axis, and this will be equal to differentiation with respect to z axis only, z only, 10x squared plus 5y squared minus 3z minus, okay, let me omit this, if it say z only, this is not z, so minus 3z square. So on differentiating, as before, when we getting that, it is considered as constant. This one also we can consider as a constant. So differentiation of constants is equal to 0 plus 0, and here you get minus 6z. So electric field at point 3 becomes equal to plus 6z, and this is equal to value of z, this is given you 3 meter, so let me put into 3, and this is your volt per meter. So electric field along, z axis is equal to 18 volt per meter.